Basically, I'll talk about machine learning and the architecture that we are having at SupportLogic. So yeah, this is me. Basically, I'm working in SupportLogic and I have ML-based industry experience of 8 years. And going towards the outline, so we'll be covering AI at SupportLogic, what's our data pipeline, and ML as a service, what we use as an architecture, then what all are the ML engines in the SupportLogic. Now, this is our SupportLogic Cognitive AI Cloud. So you would have seen this in the keynote with Karan. So I'll touch base over it to let you know the main crux out of it. So basically, as you can see, we have multiple CRMs and data sources available. So these data sources are basically being used to extract the information. Now, this is completely coming out of junk. So that's where we have data extraction engine coming into the picture. The data extraction engine is responsible basically to extract the information. Plus now consider what type of information is coming. It's voice, it's mails, it's chats, and then it's n number of sources. And from that, we have to get the context. We have to get the right information out from that. So that is important. And that's what data extraction engine is performing for us, completely removing all the junk information and getting out the right information that's available, that's utilizable for us. And now that's one part of it. The second part of it is to transform it into the readable format that can be utilized by our engines, the upcoming engines that's there. So to transform it out, we have a standard data input format that need to be performed because we have multiple CRMs, multiple types of formats, and it can go round around as we integrate more and more things, input and output. So that's where the data engine is also working to standardize the input and output formats, cleaning up, then PII removal, masking. That's more important with respect to the security and performing all the guardrails with respect to the data so that it's not getting compromised. So that's where data extraction engine is. Now coming towards the second engine, that is signal extraction engine. So signal extraction engine is basically utilized to extract the signals. We have 40 hot signals available and we are continuously adding more signals as we grow, and we are uptraining the existing signals as well. Now coming on to the signal extraction engine, this engine is basically utilizes for sentiment analysis, and we are extracting the signals out of whatever data we have that is coming in our data pipeline. It's running continuously. And if you'll talk about the ML prediction, so last year we did nearly 3.2 billion ML predictions. So this is a huge number just going through our data pipeline for our ML models. And I'll talk a bit about the architecture in coming slides that will give you a more insight of how it's scaling up and what type of load we can handle and how we can handle it out. And coming next is the context engine. This is a engine which is responsible to adhere onto the context of the information that's rolling out in the platform. Basically, complete cases and account information and all. So today we are in the world of Gen AI, and Gen AI works on the context. If you have not context, you can not use the Gen AI, you cannot use the newly trending LLMs and all. And the number one limitation comes is the context. It forgets the context if you are refreshing the sessions. So that's where the context engine is very important for us. And we are maintaining our in-house context so that we can utilize it as we want. And no matter what Gen AI is coming into the picture, we will be having our own format, own context, and we can utilize it as we want. So that's where these three engines are very important. And on top of it, sets our agents, which are utilizing all these three engines basically. And I'll not talk all agents, basically Karan covered most of them. But yeah, these agents are utilizing the engines and completing our complete orchestration mechanism and workflow that is available in-house. And that's what we call cognitive AI cloud. Coming towards the next, so this is our complete tool set that we have available in terms of core SX, assign, elevate, assist, expand, resolve SX. And the arrows that comes here are the ML tools or technologies which are available. So basically, around the platform, we have multiple tool sets, and multiple tools have multiple ML models working here and there. It can be statistical models, it can be deep learning, classical, Gen AI. So there are multiple types of models working all around the platform. So this is principles of AI that we follow at SupportLogic. We follow three main principles, and these are hard for us. So what we do is we feel that AI at SupportLogic is invisible force. When we say invisible, it's like an electricity for us. So basically, electricity powers up the appliances, powers up the things, and you get the outcome out of it. It's working in the behind, and you cannot see it, but you can see the outcome. So that's how the AI is working in support logic, where it's working in the behind, and on the UI, you will see the impact out of it. It will not get hindrance to the humans, but it will perform the enhance and perform enhancement to the UI and the end user experience. And then comes the explainability. So as we are moving towards the Gen AI world, the explainability is vanishing up. We have so many predictions, we have so many generations, but we are not able to explain how it's happening, why it's happening. Explainability was the hot topic around 4 to 5 years back, but now it's going downstreams. But here we still feel that explainability is very important for us. And that's where we work as we develop the models, as we grow in the ML field, we keep contact with it that we are able to explain as much as we can. And as we saw in the previous demos, there were multiple areas where we were able to explain the AI, why it's performing this, why it's performing recommendations, why the attention score is coming like that and all. That's all available in terms of explainability. And that's where the factors are coming up and we are utilizing them for predictions and giving the right set of scores and quantifiable measures. And then coming up is adaptive. So why we call is adaptive is basically we can evolve the models as we grow. And the basic problem that comes under the ML stream is data drift and domain contextuality. So we are adaptive to it. We can fine tune the models basis the domain. And we have a feedback mechanism available in most of our models that allows us to be overcoming the data drift problem. And as the data is coming, as we are growing, and as the world is revolving, the context of the information keeps on changing. And that's where the models should be adaptable. Given the size of models, the quantifiability of the models, we should be able to perform that out. So that's where we call our models are adaptive in nature. So this is a small snapshot of a data pipeline. It has a big picture behind it, but I've tried to consolidate it out. So just as you can see the CRM data. So all the CRMs that were available in the data extraction, first before the data extraction are there, we use the connectors to get the data out of it. And then that they got transformed and converted into the universal data format that we call support logic schema. And then comes our machine learning pipelines. So machine learning pipelines has some of the PII and masking, then signal extraction, our prediction and generation mechanism, and feedback auto training. So this feedback auto training is something that we are focusing a lot and we are trying to reduce the human efforts into it. The reason behind is so that we can provide a better experience and fast auto training. So from the downline of 7 years at Support Logic. So how we have transformed is earlier we used to manually annotate it, perform the synthesization of the data to uptrain the model, and we have multiple releases to bring up certain signals or some type of models to the production in terms of updates. Now those feedbacks are becoming completely automated. We have in-house automation available that automatically uptrains the models. When I say automatically uptrains, what it performs, it the feedback that is coming from the customers, the acknowledgements and rejections, we are storing them out. We are performing auto QA basis support logic definitions. I'll talk more about it in my signal extraction slide probably, but just to give a gist out of it, after we are getting that feedbacks, we are performing the definition check, so basically a QA check on those feedbacks and utilizing them to generate more synthetic data and perform the auto feedback training to push our models to a next level so that we can have a better precision and accuracy for our signals. So coming up is our ML architecture that we call it as a ML as a service. So it has two parts. First is a customer VPC part where we have app containers and virtual machines running up, which consolidates and separates into a logical layer we call VPC so that it's not going towards the security issues. And all the complete architecture is now going towards the ML. So what we do is basically each customer is standing under the VPC. They are trying to, we have a central API management where they connect with the ML services. And in the ML services, we have a event driven architecture that kind of a serverless architecture. So the benefit of it is basically we have done in the last 1.5 to 2 years pivot onto the architecture. The reason behind was basically the Gen AI and the amount of data flow that we are getting. And definitely you cannot see that change in the UI, but from the backend point of view, we have seen a good amount of load handling onto it. So now, given a event-driven and serverless platform, we can scale the system as much as we want horizontally as well as vertically. And we have converted all our services to ML as a service mechanism, which allows us to utilize it in numerous ways. Probably in coming future down the line, we can provide it as a platform as well, where you can directly utilize this and integrate multiple ML offerings directly to the system and you can utilize it. So that's where the thinking of it came into the picture and we designed this architecture. So coming next is the ML engines. So I'll talk more on granularity of what exactly are the engines, although the functional part of it is covered by Kritika and Karan. And you have seen multiple demos, but what exactly is happening in terms of ML behind it, that I'll gonna cover into it. So the first one is signal extraction engine. So as you can see in signal extraction engine, we are performing first of all text cleaning and pre-processing. So this cleaning is different from what data extraction engine was doing. So data extraction engine was trying to perform the junk removal and getting the right information to the system. Now to extract the signal, we have to perform multiple more steps to bring it to a fashion that can be utilized by our ML models or for processing it out. So when I say utilized by our ML model, that means it has to be tokenized, it has to be performed lexical analysis, then it has to perform into the embeddings. We have to do chunking and we have to do multiple steps that are involved to process in a fashion so that it can be classified into signals. So that's where text cleaning and pre-processing is coming into the picture. Then we have our embedding layer that is performing the embeddings of the sentences or whatever cases we have, we are converting them into embeddings that can be ingested to the model. So now this is the embedding is our LLM model. So when I say LLM model, don't confuse it with the new Gen AI models. All like LLM has been there past stages. So all LLM models are not Gen AI, but all Gen AI models are LLM. So this is not a Gen AI model. This is a LLM model that's performing the embedding out of it. And once we create those embeddings, so this embedding is coming out of our vector corpus that we have. We are not using an open source mechanism. So we have our own data available in our house that creates embedding that is contextual enabled, that allows us to get the context customer specifically. And then we have at last classification model. So classification model has multiple logics available, which is converting it into a sigmoid layer. So each layer, each node is a signal for us. And as you can see, some of the signals are being represented there in the top. It's not a complete list. We have many more. But yeah, the combination of all these sigmoid provides us if the particular input that's being provided to our signal extraction engine has a certain signal or not. So that's where the signal processing comes into the picture. And then the important part that we have made to the complete automation comes, that is the feedback. As we are getting the feedback from customer for acknowledgement and rejection to the multiple signals, we are utilizing that feedback for making our signals more precise by automation. And this automation involves utilizing those feedbacks, performing auto QA so that it adheres to the support logic definitions. When I say support logic definitions, that means, for example, let's take urgency. Now, urgency can have multiple definitions and it can go very beyond. Like urgency for some some people can be like any small thing can be very urgent, like wherever it is coming, we have to do it as soon as possible. Just move it to urgency. And so for some, as soon as possible, like end user has a behavior that they want everything very soon. So you will see more urgency tags coming up if we do something like that. So we try that the agents are not bombarded with multiple signals, especially the signals that comes with the risk into it. And that's where the definition come into the picture so that whatever is pretty urgent for us, only that get highlights in the dashboard and the agents are getting the real insight out of it. So that's where our support logic definitions are being used for auto queuing the feedbacks. And once those feedbacks are being analyzed, we are trying to analyze how much of similar data we want, and then we generate the synthetic data which surrounds like them using our explainability criteria and weighing each of the sentence word around it. And then we perform the auto training so that the new model that's coming into the picture has that the feedbacks that are there that are incorporated. So that's where the feedback is coming into the models. So this is the sentiment agent that is utilizing the extraction engine. So all our agents are utilizing the different basically engines. So this sentiment agent is responsible for extracting the sentiments. And as you can see, this was a case and we were able to extract the sentiments. And now the sentiments has been grouped into multiple categories, like we have commercial category, we have risk, we have positive, negative, then we have urgency. So yeah, this is just a snapshot of how it looks in the UI. Going towards next is the scoring engine. So before going into the depth of scoring engine, I'll try to understand what exactly is scoring and where we are using. When you see attention scores, when you see sentiment scores, when you see account health scores, all these are scoring engines, basically the scores that are being provided by the agent. And these are correlated to each other, not directly, but indirectly. So when I say correlated, I'll come to that bit later once I uncover how it's being built and what exactly we are performing over it. So basically, the scores are coming out of the complex set of features that are very complex in nature, and we have designed certain heuristics that are in combination providing us the scores. So now we cannot perform average of it. So consider a scenario, given an account, we are just accumulating all the signals, or we are accumulating all the patterns and we are averaging it out. You lead out to a very average number in most of the accounts. The reason behind is if you are performing 10 plus 20 plus 90, it's gonna give you somewhere around 40, 45 average. And then if you are doing 35, 40 and 45, then again you are getting same average. So that's not gonna work. So that's where we are using those heuristics and converting into a CDF format. We are performing a cumulative distribution function over a time series based function. So that allows us to penalize it and incentivize it accordingly, and eventually leading the score to become up and down. Now, coming on to the factors, it's not just the signals that are performing the attention mechanism score or sentiment score you are seeing here, but there are multiple other factors. If you'll see the channel communication, how the time is being there on over the case, what's the history of the account, and how is the inbound and outbound comments are going, how is the frequency of the signal. So when I say frequency, it's not about just okay, it has 5 signals, it has 10 signals, that's it, but how it's growing over the time. So over the first 10 minutes, just giving an example, don't take it like it's the algorithm. So just over the first 10 minutes or 5 minutes, were there risk signals or were there positive signals, and how it eventually led to the end. So that's how all the time series based analysis going into the distributive function leading to the scores. And that's where the attention score, sentiment score, and account health score comes. So I believe somebody asked, like, it's just maybe in the training session, like how is the account health score is coming in. So account and score is utilizing signals, then again channel inbound, outbound, then how is is there a churn risk or not, is there escalations or not, and how many agents have interacted, how many agent transfers has been there, how many participants has been interacting over the case. So multiple things are accumulating up, and it's not just plus and minus. As the case grows up, as the case comes into the ends, the scores of over the case changes, and score over the account health also changes. So next coming up is our prediction engine that we are utilizing in escalation management. So basically this engine utilizes our gradient boosting classifier. This is a very strong classifier, and there is a very strong reason utilizing it, because this particular engine has a very huge set of features. So when I say very huge, it's not just you are seeing data, very data, four trees coming up and bringing this model. This is just because I have a short size in the PPT. There are around 60 to 70 such trees and decision terms coming up to bring this ensemble models. So when I say 60 to 70 trees, what does that mean? It's not that plant that is growing outside. These are the decision trees that we use in classical machine learning. And each tree is responsible to bring some of the inputs and some of the errors. Now you can see there, like each tree is providing some output to ensemble predictions, and then they are being utilized by second decision tree as well. That's where the mechanism is trying to utilize the information that is being provided by previous tree, and it's trying to reuse it with extra information to bring some more accuracy onto it. And the other point is all the trees does not have the same information available. Probably just giving an example, first tree might be utilizing two to three features. Is there an escalation, or how was the case started? What were the skills involved into the case or not? And probably the other ones might not be using it or maybe using it. So that's where each decision tree tries to perform more and more information gain, and each information gain results into the escalation prediction. So now this prediction engine results in the escalation agent, and you can actually see what were the factors that influenced. Although in, if I talk about sentiment score, attention score, all the factors that you'll be seeing, those will be the highest impacting factors. That's not the like always factor, like only two or three will be the impacting. There are 10, 12 more factors that has a lower weightage, but at some point they are interacting. So consider an example like I am giving 100 score for a weightage, and I am providing you five information here: customer escalate frequency, high customer urgency, and case age activity, poor support responsiveness. Now these five may constitute 60% or probably 70% of the weightage, but there are 30% of it that doesn't mean to be showed on the UI, but indirectly impacting towards the contribution of escalation. So that's how escalation engine is built. What we called is LT on the UI. So coming on to next is recommendation engine. We call it case routing agent as well. So recommendation in, so why we call it recommendation? Because it is having a recommendation engine behind which is empowering which agent to perform. So now we are using here content based filtering here. So recommendation engine comes with two types of engines. We are using content based filtering. And why content based? Because we have multiple categories available, as Kritika covered. I'll not go into functional mechanism of it, what is time overlap, how it's being calculated, and what skills and all, because you guys have already seen that out. What I'm gonna try to explain it out, it what exactly behind it is. For example, let's take skill score, and then we have agent skills and case skills. Now the question comes, okay, boss, I know you are having some case skills and agent skills you are performing matching, but the question is from where these case skills are coming up. I know you, I can add manually, but how you are doing it? So what we are doing basically is we are trying to extract the important tags out of it. We are performing some ML tagging theorems and NER theorems, which allows us to get the exact tags that can be potential for us. Now, when I say exact tags, is it the time, place, animal thing? No. Given a support domain, we understand what would be the tags and what would be the skill set that a agent will be utilizing, and we try to find those skill sets in the case. And once we find that out, we tag those skills into the cases. Now coming on, this is the first model that tags just the entities over the cases. Now, because the case is new and we have been into this from ages, now we can also understand that given these two skills, there is a high possibility it will have four or five skill as well. So we give that weightage to the case that, okay, boss, two and three, basically one, two, three skills will have higher weightage, and then three and four will also be likely to coming. So let's find an agent which has all these five skills, and that's where agent skills and case skills start matching up with the probability function, and we get the skill score. Now, somebody asked from the audience that what if the content is not available much in the case, it's more technical, and how it's gonna happen? We don't need to worry. We have five, like total five contributing factors that are providing us the agent recommendation. No matter if skill score is not available, we have other four. We will utilize them. We will utilize those weightages to get the right agent for us. And that's where let's talk about the next one, that is a customer history. So now what we try to understand is what exactly has been the history of the customer and how an agent has performed. So what we try to do is from the point agent got allotted to the point it got disengaged with the case. For example, a senior agent came into the picture because it got escalated. Now that escalation negative point will not be added to that agent because it arrived post that. But if an agent is already solving that case and then the escalation got assigned, then that point will be counted to the agent. So that case performance is added to the agent that allows us to identify if how is the ranking of that particular agent for that particular customer. Now, coming on to the bandwidth, into this, we try to take a gist of agent backlog and incoming cases and try to identify if an agent has the bandwidth or not. So, it has a very basic statistical theorem behind it that we try to utilize, which tries to check the backlog and which try to utilize incoming cases that are available in the queue for that where the particular agent is assigned for. And it just not utilizes this for this particular agent, but it waits it out for all the agents. And if all the agents has same skills, so now bandwidth and skill score is being correlated. How? Given if the skill is available for all the agents, we will see, okay, this skill is available for all the agents. Let's cancel it out. And then maybe some of the agents will not be available and we have to see bandwidth for only the three agents. So that's where kind of correlate with each other. And coming on to time overlap, then we have the time overlap available for agents. We can set the window and we understand each customer's timing as well, depending on the account history. And we try to perform that time distribution. And over it, we matches up what exactly would be the feasible time where a customer as well as agents will be available. All these basically contributes towards recommending us what would be the right agent. And then the recent assignment penalty is our decay function. And decay function is responsible that we are not penalizing a smart agent for the getting things done more and more. That's where I believe the information more about like how we can configure it and that was covered in the previous session. I'll not go into that. So coming on to the recommendation score, now we have all these five coming up. All these have weightages. We can configure these weightages depending on are the responses and answering the right information from the knowledge base. So how it's being configured is it's not like we are just typing up the query and it's bringing up similar to the available generative models, but we have well designed it from the format of enterprise so that we are in a domain of support and we are utilizing it in a proper factual basis. So when I say proper factual basis, let's try to understand it, how exactly it's working, what exactly are the steps that are involved. So for example, a user query came and into the complete system. So that query will again be processed via language processing system. Again, signal extraction has one processing system. This processing system will be completely different from that because this model might be needing certain other extraction out of it, certain cleaning and certain more conversion of English statements, or I would say the human readable statements into a machine readable state. So that all will be performing in the language processing. And once that is done, the pipeline that is going from below is our knowledge sources. So each customer has its own knowledge source. How it's being designed is we are converting and creating the knowledge articles out of the cases, which are being utilized by our this Resolve Essex platform to provide agent information that how he can go ahead and what else information he can utilize from the documentations. So this knowledge source comprises of the existing knowledge articles plus the articles that we are regularly creating with the conversations. So now, given the query, we process the information, we checked our knowledge DB. So now knowledge DB is utilizing RAG architecture here. So when I say RAG, we have all the data available in a vectorized format. While in the vectorized, that provides us a better mechanism to sort it out and search it out. And we are able to perform it fast. And now, once we are able to get top 5, top 10, whatever we want to get, we utilize the input query with the available information and utilize the LLMs with our prompt modeling system. So when I say prompt modeling system, we do not have a static prompting mechanism to retrieve the required information. Rather, given what is the context going on. So remember I talked about context engine. So that comes into the picture. Given what exactly the context going on in the complete case, it tries to identify right prompt, and that prompt will be responsible to utilize input query with the knowledge articles to provide us the right answer that can be utilized for us. So this is the complete loop that brings up to the answer engine. Now, given support domain and given an enterprise usage, we have guardrails there. So this guardrail is responsible because we cannot be toxic in nature. We have to be very factual and contextual in nature. So this guardrail is performs the fact check with respect to the knowledge sources that has been extracted from the knowledge database. Now, suppose the LLM generated some information. That information can be vague. So we cannot show that up directly to the end user. We will perform a fact check on it. We will score that out, and if it passes our threshold, then only it will gonna combine into a resulted generated answer, and then we are gonna show. Otherwise, we're not gonna show, and that's gonna go into our feedback loop for upcoming iterations where we will gonna uptrain our maybe a prompt model, maybe or maybe knowledge sources. So there are multiple challenges to it that the usual LLM models has, which we have tried to solve so that we can utilize it more efficiently. And that's where the knowledge agent that was discussed, and probably you'll see more about it in the next session. So we have resolve assist there where we can understand what is the problem, what are the current status, what is the next steps, and then we can utilize response assist to generate the response. We can see the knowledge assist to understand what all the knowledge articles were there that are being used. And at the bottom, we can see the tags available that allows us to tag it out for future, so that if similar type of queries are coming up for a particular account or maybe for a particular customer, we can utilize that information, we can generate the knowledge articles out of it, and we can provide more precise, more better answers to the agent. Yeah, that's where knowledge agent comes into the picture. And I believe, yeah, this comes to the end, and this completes all our core SX assign, elevate, and expand assist and resolve SX.